So thank you all so much for joining us. It is roughly 2:15 p.m. here in New Orleans, and we are having our second press conference of the day on stars, protostars, and more clouds. My name is Kerry Hensley. I am the AAS Deputy Press Officer, and I am joined today by the AAS Press Officer, Susanna Kohler, and the AAS Media Fellow, Ben Cassess. I ask you to take a moment right now to silence your cell phone or anything else that might make noise and interrupt our press briefing. We're going to have two press releases distributed related to this afternoon's press conference. The press releases related to this morning's press conference are on our AAS Press Twitter account. They're also on Slack and in the press kit, so you can look for them there. So briefly, ground rules for those of you who haven't attended a AAS press conference before. I'm going to briefly introduce our topic and our panelists. We're going to hear from them in order, and we're not going to break for Q&A in between the presenters. We're going to have Q&A afterwards, where we can direct our questions to all four of the presenters at once. And I ask that you not clap in between the presentations. You'll have a chance to thank all of our speakers at the end. And finally, for those of you who are watching remotely on Zoom, please use the Q&A feature to queue up your questions at any time. So as I said, this is our Stars, Protostars, and More Clouds press conference. We're going to be hearing from four speakers today. In order, we'll first hear from Elena Orlando from the University of Trieste and Stanford University, speaking on asymmetric gamma ray emission from the quiet sun. Following will be Anugu from the CHARA array and Georgia State University, speaking on a colossal star erupts, examining one of the largest stars in the Milky Way as it fades from view. Next, we'll hear from Cheng-Han Hsieh at Yale University, speaking on early evolution of planetary disk structures that are seen for the first time. And finally, Nicole Karnath from the Space Science Institute will speak on the wondrous 3D world of protostellar shocks in NGC 2071. So with that, I'd like to invite Elena to come on up and get us started. And hopefully, sorry, so many technical difficulties. Hopefully that's all gonna work great. Thank you.
Okay. Good afternoon. So what you see here is a wonderful image of the quiet sun in ultraviolet. However, today I'm going to show you the asymmetric emission from the quiet sun that we have observed with the Fermi telescope in gamma rays. I'm Elena Orlando, and I present also on behalf of Bruno Arcioli, who cannot be here today. And a few days ago, this work has been accepted to be published in the Astrophysical Journal, and it will appear later today on arXiv. So I'm going now in more details. Current understanding of the quiet sun in gamma rays tells that the sun emits continuously and uniformly across the disk. However, today I'm going to show you that we did observe significant asymmetry in the gamma ray emission from the quiet sun. These are our gamma ray observations of the quiet sun, seen with the Fermi telescope. On the left, the low energy gamma rays. On the right, high energy gamma rays. The dashed circle represents the solar disk. And you clearly see that in both images, the gamma ray emission is asymmetric. And in addition to this discovery, we also found that this asymmetry occurs during the moment where the magnetic field of the sun flips. So I'm going now into the details, and I will explain you all these concepts from the beginning. You all know that the sun is is emitting, and it's also can be very active in very short timescales, and we call them flares. In this analysis, we excluded all the flares, so that's why we call it the quiet sun. But how can the quiet sun emit gamma rays? It is believed that the quiet sun emits gamma rays from continuous bombardment of galactic cosmic rays. Galactic cosmic rays are energetic particles that are coming from beyond our solar system. This that you see here is the first image of the quiet sun that we have in gamma rays. And this is how we discovered it back in 2008 by using the Egret telescope flown from 1991 to 2000. And this was previously then the Egret, the Fermi mission. The sun is the yellow spot at the center of the image, and it is brighter than the rest of the image. Nowadays, instead, we have the Fermi mission with its Large Area Telescope, which is orbiting Earth and taking gamma ray data since 2008 with much higher sensitivity and angular resolution than Egret. Fermi detects the sun almost daily. To the left, you see Fermi, and in the background, you see, starting from the bottom right corner, you will see the sun that crosses the gamma ray sky. Here it is. And here, one more time. And this is the sun seen through the eyes of Fermi. This plot shows the solar activity. And you can see a peak of the activity almost every 11 years. And this represents one solar cycle. The Fermi telescope has covered this entire solar cycle from 2008 on. And here our discovery comes. In this time period, we have studied the emission and the morphology of the gamma ray emission from the sun over time and how it changes over time for the entire solar cycle. We found a symmetry in the emission at low energies and at high energies. In particular, this asymmetry is found at the peak of the solar maximum. It is exactly this time interval where the asymmetry is found, the black region. It turns out that in this very same time interval, the magnetic field of the sun has flipped. To the right, you can see the visual of the flip. So, in conclusion, our finding of the asymmetry exactly during the flip suggests a crucial role of the magnetic field, and it opens up a link among different disciplines: astronomy, particle physics, and plasma physics. However, the physics of our discovery goes still unexplained, but because the flip happens almost every 11 years, we expect to see a similar behavior also in the next 1 or 2 years. Thank you very much, and I hope this discovery is exciting for you as much as it is for us.
Hi, my name is Anugu. I'm from the Georgia State University. This afternoon, I will show you first images of a gigantic star, which went to a vast eruption. The star name is RWCFI, which is a very massive star, which is around 1,000 times more than the size of the sun. In fact, it is one of the largest stars known in our Milky Way galaxy. If we put that star for scaling in our solar system, at the center of our solar system, it would extend larger than the size of the orbit of the Jupiter. So it's a very large star, and something remarkable happened last 2 years for this star. So this plot shows the visible brightness of RWCFI, which dimmed very dramatically. And it reached a historical minimum in 2022 and in December. After that, starting from last year, 2023, it started brightening again. And we were wondering what is happening to that star. And in order to understand what is happening to the star, we need a close-up imaging or close-up observations. And unfortunately, the star is so far away, which appears very tiny to us. So we need which is around, actually, to scale, it is 1 million times smaller than the size of our full moon in the sky. So it's very small. In order to image this one, any conventional telescope is not sufficient. It does not have the sufficient angular resolutions. That's why we had to use the CHARA array, which is the world's largest optical interferometer, which works in optical and infrared wavelength spectrum. CHARA array is located in California, which works by combining lights from 6 telescopes and makes the aperture synthesis images. If you see the white ellipse, that is the size of the effective diameter it will make. For comparison, you can see the center of the there's a big telescope that is 2.4 meter telescope in the picture. So it is in the end, CHARA array makes 330 meter diameter telescope. So we use this telescope to image the RWCFI, and these are the images. The left-hand image is the image we obtained when the star is very dim, when it is faintest, and the right-hand side image is when the star started brightening again and in the middle way, 8 months later from the faintest point to the when we took the second image. And we saw when we recorded the first image, that was the first image of the RWCFI. And when we saw that it is asymmetric and distorted, so we were wondering what happened to that. And so the second image reveals that in the first image, the west side or the right side of the image is fainter. But when we see the second image, the right side image is brighter. A fainter thing is moved to, or appears to be on the top side. We think that most promising explanation to explain the images and the dimming of the RWCFI is the solution or the theory offered to explain the great dimming of Betelgeuse. Arc convection, the theory is that the hypothesis is that yeah, it is for the Betelgeuse case, it is observed that art convention cells power the ejection of surface mass ejection from the stellar surface. And this gas cloud is enormous, and it will travel outwards the star and cools down and condense into dust particles. And this dust is very effective blocking the star. So the dust is in between our line of sight and the star. That's why we see the dimming. And the dust is also orbiting the star. So that's why we started brightening again when it is out of our line of sight. In summary, I say that CHARA array angular resolutions are very powerful to image the this colossal eruption, and the images explain why the dimming was happened. These are kind of observations are very essential to understand how the mass loss happens into the aged stars, which are red supergiant stars. And these mass loss rates are very important to, it has very large consequences how they stars end up as a supernovae, and also and after that how they end up their properties, whether they are neutron stars or black hole remnants. Thank you.
Hello, everyone. My name is Cheng-Han Hsieh. I'm a grad student at Yale University. Today, I will share our campus result, early evolution of planetary disk substructures seen for the first time. Planets are born in disk made of dust and gas, known as protoplanetary disk. Recent observation by the Atacama Large Millimeter Array, ALMA, has revealed beautiful rings and gaps inside these protoplanetary disk. Studying these substructures is very important because they are possible formation site for planets. And it is one of the big questions of planet formation is trying to link the morphology of these protoplanetary disk, the rings and gaps, with the planets we know today. It is important to point out in observation, currently previous studies predominantly target large luminous disk or more evolved disk with age greater than 2 million years. Until today, we do not have a large uniform high resolution search of these substructures for the youngest class 0 and 1 disk with age less than 1 million years. This is partially because substructures in younger disk are very hard to find. The recent ALMA large program eDisk survey led by Hsieh in 2023, they surveyed around 20 sources, and as you can see, most of the 20 sources shown on the right, most of the disks are smooth. We do not see rings and gaps. So this is because substructures are rare in the youngest disk. However, finding them is very important because they tell us how early does these substructures form, and as a corollary, how early planet formation begins. So, introducing our campus survey. So we use the Atacama Large Millimeter Array, ALMA, the largest radio telescope in the world, to survey nearly all the embedded protostars in 7 nearby molecular clouds: Chamaeleon 1, Chamaeleon 2, Ophiuchus, Ophiuchus North, Acridia, Coaustralius, and Serpens. We detected down to an extremely high angular resolution of 15 AU. This is around 3 times the distance between the Sun and Jupiter, and with a total source around 90 protoplanetary disk. With this large sample, we, for the first time, were able to determine when these substructures appear, and we are able to study how these substructures evolve. So we arrange the protoplanet disk with substructures by age. So on the left-hand side shows younger sources, and on the right-hand side, older sources. So interestingly, we start to see substructures in the class 1 stage with age around 0.2 to 0.5 million years. This is possibly telling us that giant planet formation begins at the very early stage after protostar formation. In addition, looking at our sample, we found that disks with multiple rings morphology are generally larger. And more interestingly, we found there seems to be 2 populations of these substructures. One is like donut shape with a large central cavity. And the other type of these substructures are centrally filled. And these raise like interesting questions of like what kind of planetary systems will these 2 populations evolve into, and which type of like disk will evolve into our solar system. So these are like open-ended questions that we will research more in the future. And in addition, we look at all the multiple ring systems, and we found all of them tend to be centrally filled. We do not see a large central cavity in the center of multiple ring systems. This is something very interesting and something we will look further in the future. And here is my take-home message. So from our campus survey, we surveyed 7 nearby clouds at an extremely high angular resolution of 15 AU. And with 90 protoplanetary disk, we found these substructures only start to appear for sources with age around 0.3 million years. This is possibly give us a time scale for giant planet formation. And also, from our samples, we discovered 2 populations of these substructures. One is a donut shape with a large central cavity, and the other one is centrally filled. In addition, we find that multiple ring systems tend to be centrally filled. So the 2 populations of the substructures raises a lot of interesting questions, such as will these disks make different planetary system architecture? Will one population evolve into our solar system than the other? So these are like interesting questions we will investigate in the future. So that's the end of my talk. Thank you.
Hello, my name is Nicole Karnath. I'm a research scientist at Space Science Institute. And today I'm going to be talking about the wondrous 3D world of protostellar shocks in NGC 2071 IR. So we use 2 telescopes to make this work possible, Sophia and Hubble. And some backgrounds, NGC 2071 IR is a star-forming region. You can see the image on the left is an visible or optical image, And buried inside those dark clouds are stars that are forming. So if we look at this with some infrared wavelengths seen on the right, you can see individual protostars and also a lot of material around them. So when protostars form, they start launching jets and outflows, and that material is blown into the surrounding molecular cloud that disrupts the molecular cloud, that affects feedback, turbulence, very interesting things. And it can either trigger or shut off new stars to be forming in the region. So there's two big stars that are forming that we were going to focus the study on. That's HOPS 361A and HOPS 361C. And you can see they're encircled by white circles, and they're both driving two outflows, which are highlighted here. Both of these stars are also what we call intermediate mass protostars. So they're bigger, they're going to form stars bigger than our sun. And they're very important because they're powerful enough that they can drive powerful outflows that impact the surrounding molecular cloud, but they're not very well studied. So big, massive stars are sometimes more well studied because they're very bright and they're easier to see. But fewer intermediate mass protostars have been studied in the literature. But they're very important because they bridge the gap between low mass star formation and high mass star formation. So it's really important that we understand how these things correlate. So here on the left, we have a plot of the force of the outflow from CO data against the x-axis of how luminous they are, the bolometric luminosity. So you can see that we have several low mass stars and fewer intermediate mass stars. So we want to know if this trend of linear space and log space holds for all intermediate mass stars and if that connects up to high mass star formation. Intermediate mass stars are more common than high mass stars, and they're also far more powerful than low mass stars with these outflows. But we need to assess the driving forces from these intermediate mass protostars, understand how they can affect star formation efficiency in their clouds, and drive turbulence in these clouds. And the best way to do that is to understand the 3D kinematical picture of outflows into these molecular clouds. But 3D kinematics is extremely difficult because you cannot find all 3 dimensions with one instrument or one telescope. So that's why we use SOFIA and Hubble. And combining these two gives us this 3D picture. So we propose time on both HST and SOFIA in the near and the far infrared to focus on the outflows in this specific region. And with this, we can determine the 3-dimensional shock velocities that are being driven in this outflow. We can use models then to constrain the velocities of these shocks, estimate how much mass is being thrown out of these stars, and how much momentum is being injected into the surrounding medium. We can also constrain these velocities and mass flow rates to understand the jets and the winds launched by these intermediate mass protostars. So we split this into 2 different studies, focusing on HOPS 361A and then also 361C. And this used discretionary time with HST and also SOFIA using GREAT. So here on the left, we also were able to use an archival HST image. So this was very, very important for our work. So this is an image on the bottom taken in 2009. And you can see this is focusing on the outflow from HOPS 361A. And we got a new image in 2021 of the same region. And you can see from comparing these 2 images, the region has changed dramatically. Some gas is there in 2021 that wasn't there in 2009. You can see some things have moved around, some things have changed in flux and brightness, and some things appear that aren't in the 2009 image. So this is already a very interesting region, showing that these are very dynamic and quick interactions with the surrounding environment, which is very important to study. So starting with HOPS 361A, it has a very compact and very complex or messy outflow. So one really interesting thing we noticed pretty quickly is that they had these rigid structures. So they look the same between the 2009 image and the 2021 image. And you can see that the flux is pretty much the same. The structures or the morphologies of these regions are very similar. We identify them as rigid regions that we label 1 through 9. And these we think are kind of tracing the outflow cavities, so that the bounds of the outflow being launched themselves. For HOPS 361A, we found that the knot speeds of these moving motions are actually quite consistent throughout the entire outflow. And we can constrain the shock speeds to be about 50 kilometers per second with our models. The proper motions that we got between the two Hubble images range between 90 and 275 kilometers per second. And this cavity is not as cleared as the next one I'll show you, HOPS 361c, which means it might be less evolved, even though these stars are very similar in mass, and we think that they're forming at about the same time, and they're very physically close together in the same molecular cloud. So as I said, it's a much more complex region. So this is a speed map. So we had to identify the individual features that were changing between the 2009 image and the 2021 image. So here we identified in the green boxes or circles 13 individual regions that either had very clear knot motions or very clear changes in flux. So this is where we got our knot speeds from, and each individual arrow is showing the motion of the region. And you can see that more or less it's moving up and to the left, but there's definitely a few arrows that are pointing in the opposite direction, which is very intriguing because that's not something we necessarily expect to happen. We expect most of the outflow material to be moving all along one axis and maybe expanding out, but not necessarily moving in a completely different direction. So this is telling us that this region is very complex and it's very messy, which now that we have learned more about protostars, we can actually say that they're very messy when they form. HOPS 361c, we published this paper with a colleague, Adam Rubinstein, in 2023. And this protostar itself is less luminous than HOPS 361a, and the outflow knots are much more distinct. You can see them labeled 1 through 11 here, and they're much fainter than what we see for HOPS 361a. The outflow for HOPS 361c, you can see extends much further out than for HOPS 361a, and it extends about 0.2 parsecs, which is quite large. You can also tell it has this arc motion, and that's very interesting because that's consistent with HOPS 361c being a binary, which was resolved in John Tobin's work from the VLA and ALMA in 2020. And we fit some models to this and found that there's a precession of this outflow axis that rotates about every 2,000 years. And the opening angle of this outflow is about 16 degrees. So that's an interesting number because that's actually quite narrow. And as we've seen in other talks, we expect the opening angle to expand as these stars evolve. We also found that as the knots get further from the central protostar, they actually are losing speed. So they're decelerating, which was not the case in HOPS 361a. The proper motions we found for these 11 knots range from 100 to 350 kilometers per second. And the shock speeds are about 50 kilometers per second, again, using our mappings models. The SOFIA data was very important because it allowed us to obtain the far infrared, and also that gets us the third dimension. So these observations of spectroscopy added the third component, which is in and out of the sky, or the radial velocity, as we call it. So these great pointings you can see on the left show where we got great spectra surrounding or overlapping this region. And here's one example of a spectrum on the right, which is the central protostar HOPS 361a. And we did a 2-component Gaussian fit to that. And you can see the radial velocities are 4 and 14 kilometers per second, which are in line with the cloud standard of rest. So then we can use these line profiles and use the luminosity of these lines to actually put into these models and determine things like pre-shock density. So how dense was the material before the shocks came? And also that gets us the shock speeds that we used in the mapping models. So in conclusion, there's 2 outflows in NGC 2071 IR, but they're quite different even though they're being formed from basically very similar protostars. So using Hubble and SOFIA, great. We did the multi-epoch observations with Hubble to allow us to measure the knot sizes, the gradients between the epochs, do the proper motions and their velocities over a 12-year time span. And then the SOFIA great observations resolved this O1 line at the far infrared, and that helped us understand the radial motions of these down to a few kilometers per second, and added a third component for that 3D understanding. HOPS 361a is much brighter than both HOPS 361c, but they're both forming intermediate mass protostars. And the amount of material being launched from each outflow are very similar, about 5 times 10 to the minus 6 solar masses per year, which is very typical for intermediate mass protostars. But Hofstra 61A actually has a very consistent momentum flux throughout its entire outflow. Versus C, it's actually decelerating. So the material is losing energy as it's being thrown further and further from the protostar. So only HST and SOFIA actually enable this type of study to understand a three-dimensional understanding of these outflows, which is very difficult and very rare in the literature. So our community needs more space-based, high-resolution, and far-infrared capability in the future so we can continue this work and really understand how outflows affect the surrounding environment, drive turbulence, and shut off star formation efficiency. Thank you.
Oh boy. All right, so with that, we're going to get started with our Q&A portion. If you're watching on Zoom, be sure to use that Q&A box to queue up your questions. If you're in the room, please wait for Susanna to bring you the microphone. And for all of our viewers, please be sure to state your name and your affiliation and who your question is for.
Hi, I'm Clara Moskowitz with Scientific American, and my question is for Cheng-Han Hsieh. Would you say that your survey is capturing the very first stages of planetary formation, or do we believe that there's a lot happening even before these features form that we just can't resolve yet?
Okay, thank you for your question. So our survey is limited by the angular resolution. So our angular resolution is around 15 AU. So we can only detect substructures such as rings and gaps larger than 8 AU. So to put it in perspective, the distance between the sun and Saturn is around 9 AU. So if there's a gap or ring larger than the distance between the sun and Saturn, then those substructures we can detect. We don't see any substructures in the earliest systems. This might be because substructures are smaller early on.
Okay. Go to Leslie.
Leslie Sage, Nature, and this is for Elena. So I missed whether the high gamma ray emission was associated with the positive pole. And but whichever it is there a physical reason you could think of why the high energy would be associated with one particular pole?
I think the question is for me. So thank you for your question. So actually we see gamma rays during the, when we see the asymmetry of the gamma rays, they are coming from the north pole of the sun for lower energy gamma rays and higher gamma rays from the south pole. And this is the sort of asymmetry that we found, the most significant asymmetry that we found. About the question, the physical interpretation for that, actually, we don't have it right now. That's the point. That's one more mystery that adds up to the other mysteries that we have about our sun. And but we see this connection with of the emission, the asymmetric emission. So this is not isotropic emission, but it's coming from different regions. We think we see this association with the time period when the magnetic field flips, and this gives us a sort of hint that this non-isotropic emission is associated with the magnetic field. We see other spots where there is no isotropic emission, and also the magnetic field of the sun changes continuously. But this very moment when the emission is isotropic, both at low energies and high energies, is really during this this period of the flip of the magnetic field. So I hope I can give you an interpretation for that, but we still don't have it. We see this hint of this association.
This is primarily a question for Dr. Anugu, but I want to follow up with Elena or Orlando for a second, try to needle you a little bit more. This sort of continuous gamma emission you're describing is from cosmic ray bombardment of the sun. You see this polar emission at solar max. Is it reasonable to say that there's some polar influence of kind of where there's more or less cosmic ray bombardment of the photosphere of the corona? Is that probably what you're seeing?
Thank you for this question. And actually, we see a continuous emission all over the solar cycle. It's possible that during that flip, actually what happens is a very strange, I would say, particular flip, where actually in that around 2014, it's not just a moment, it's one more years when this flip happens. And in that period, the magnetic field, the polar magnetic field in the north and the south is 0. And so the associations with gamma rays, like at low energies, high energy gamma rays, can give hint on the behavior of the galactic cosmic rays with the magnetic field. So as you say, it's possible that is for sure. I mean, we know there is for sure this connection, but we don't know still yet. Like magnetic field plays an important role in deviating the trajectory of cosmic rays.
Right.
And this happens even more where the cosmic rays are less energetic and they are. So in this sense, we can follow up in future studies and also future observations, and also in theory, because now the theory predicts that the emission is pretty isotropic, because we don't have accounted up to now for the different magnetic fields and the changes in the magnetic field during time. So this is something that should be for sure investigating, and thank you. And that's one possible hint for sure.
Thank you. And I realize I did not identify myself. I'm Corey Powell. I'm here reporting for IEEE Spectrum. If I can just do a quick follow-up for Dr. Anugu. You made a close analogy between what happened with RW Cephei and what we saw happening with Betelgeuse. How similar are these two stars in terms of like mass and their evolutionary state? Are they good models for each other? And is this does this tell you something sort of more generically about how hypergiant stars behave?
Yeah, that's a good question. The Betelgeuse is a red supergiant, and RW Cephei is a hypergiant. So they are very close analogs, and they are very large, similar to 1,000 solar sizes. And they lost the magnitude around Betelgeuse lost around 1 magnitude, and this one is lost around 1.5. The similar trend. So we think that they are close, but Betelgeuse after the dimming and when it is brightened up, and the pulsation period is messed up, means it's not followed the same trend, and because the thinking was that it lifted a lot of mass from the stellar surface, and that made the star in a weird position. That's why the standard pulsation cycle was not followed. And we are for the RW Cephei also have around 45 450 days of pulsation cycle, but the dimming was it did not follow the similar to Betelgeuse. The dimming was around more than 1 year. Betelgeuse case, it was quicker. So we are yet to see if the pulsation cycle will follow for RWCFI or not. We need to follow up. It just started brighter up, and we have to see how that things go up. Thank you.
All right, thank you.
All right, we can go back to Ethan.
This question's for, oh, sorry. I'm Ethan Siegel from Starts With a Bang. My question goes for Cheng-Han Hsieh. I want to ask you, it's cool that you see evidence for structure appearing in these early disks. Is there any evidence either for or against that what we're seeing is planet forming structure as opposed to a transient feature being carved in the disk that will be washed out during the evolution of this planetary system, as some simulations indicate?
Well, that's a very good question. If you have for simulations, if you have like Earth size or like Neptune size planet inside the protoplanetary disk, they will start to accrete gas surrounding gas, and then over time they will curve out like gaps and rings. And on the other hand, different instabilities like perturbation in density or temperature can also cause substructures. So it is very difficult from observations to determine whether or not these substructures are definitely caused by planet or they're coming from disk instabilities. So this is something, there's an ongoing research, and it's currently at this moment, we cannot really tell whether these substructures are created by planet or disk instabilities. But however, it is still very important to determine when these substructures form, because it's, even though we don't know where there's a protoplanet inside, it still gives us a time scale for planet formation. Because early on, you have a very high accretion rate, a lot of gas and dust falling in the disk. So the disk is very turbulent. So in that case, the dust hasn't settled down onto the meat plant. So you only see like a smooth disk. You don't see rings and gaps. But over time, when the turbulence starts to decay, when the dust settle down to the meat plant, that's the time when you start to see substructures. So it gives us the time scale for the turbulence to decay and the dust settle to the meat plant, which is the necessary condition to form planets, because you need the dust to settle down to the meat plant, to have like streaming instabilities, and the dust start to like collide and then form larger planetesimals. So it's looking for when substructures appear, still gives us a time scale for planet formation.
We still have a question in the back here. Great.
I am Trish Murrah. I'm a freelance science writer. My question's for Nicole Karnath. It sounds like Sophia really contributed some critical aspects to getting 3D data. Now that Sophia has been decommissioned, what are your hopes or plans for how we might get that dimension back?
That's a great question. As of right now, we do not have access to the far infrared wavelengths that Sophia did. So that part of the spectrum is completely inaccessible to astronomers right now, from about 30 microns all the way out to ALMA and the VLA wavelengths. Sophia was the only telescope in the world that covered those wavelengths. And it also was extra special because it flew above a lot of the water vapor as well. So for things like GREAT, we just do not have that answer. We could potentially use other far infrared tracers that James Webb potentially covers, but that can introduce a whole nother problem of data analysis and consistency. So hopefully with some new far infrared missions that are being put on the table, we can get that regime of the wavelength regime back and then redo that. But yes, that was a big loss because especially for outflows, the far infrared that Sophia covered was very essential.
Thank you.
Do you have any questions online? Then we've got one. Okay.
This is from Bill Waller of the Galactic Inquirer for Elena. It's, why are the low and high energy gamma ray sources observed on opposite poles from each other?
I'm sorry, I missed the question. Where the low energy is?
Why are the low and high excesses observed on opposite poles?
Why? Yeah, actually, I don't know. I cannot answer to this question. At the moment, we don't know it. We think that it depends on the energy of cosmic rays, so low energy, because there's some hint. As I said before, the magnetic field of the sun affect how cosmic rays propagate and how cosmic rays are accelerated close to the sun. But there may be some, for sure, interactions, and that's the reason for that, but we don't know it exactly. We don't know the theory. We don't know the, at the moment yet. We don't have the explanation. Thank you.
All right, looks like we've got another question from Ethan, and then I've got one as well.
This question is for Narsireddy Anugu. I'd love to know, you showed side by side the two images from 2022 and 2023. But you talked about this as though it were a brightening, that it was this bright in 2022 and now it's this bright in 2023. Do we have historical observations of this that show, oh no, it was at a higher brightness and then it dimmed and we saw the dim image in 22 and then it re-brightened in 2023? And if not, like if the answer is yes, then it's just yes. But if it's not, then why would you on Earth say it's anything like Betelgeuse?
That's a great question. So we do not have large data as Betelgeuse have, but there are several years, like at least 4 or 5 years of data available in the AAVSO, and also there is a data set like 10 years ago, and they show that the magnitude or the brightness is similar to what we have in 2021, for example. And since then, it is started dimming. In 2022 December, it went to the historical faint level. But yeah, so yeah, if you compare with Betelgeuse, we do not have like hundreds of years of data, I think.
But if it was brighter,
yeah,
and then it dimmed,
yes,
now it's brightening again.
Yeah, it went to 2021 level, which is back to the normal level. Thank you.
All right, I've got a question for Nicole. Hello, this is Kerry Hensley from the AAS. This is a two-part question. You mentioned that one of these young protostars had a very narrow outflow with the opening angle of only 16 degrees, and that this angle tends to increase over time. So I'm curious, is this a function of the outflow affecting the interstellar gas and like plowing through it, or is it something about the actual evolution of the star that's changing this angle? And regardless of the answer to that question, what's the kind of time frame on which we see these outflows evolve?
Those are great questions. So for the first one, it's yes to both. It not only is the material impacting the surrounding medium, so it's actually pushing material away and out. And the shocks are pushing not only material up through the original outflow axis, but then they're also starting to push things away in that third dimension that sometimes we cannot detect. But it also has to do with the individual protostar itself. So each protostar, they're like snowflakes. They're very individual, and they might form the same mass at the very end of the day. You might have, 100 stars that form 1.85326 solar masses, but how they got to that specific point, they all have an individual story. So it definitely is the combination of both of those. So the first question. And the second question was, I forget.
Oh, like on what time scale do we
Oh,
see
yes.
these outflows evolve?
Well, the images we got, we saw quite diverse changes just on that 11-year time span. So they happened very quickly, not only in just like continuum images like we saw from Hubble, but also like a lot of chemistry is going on. Also very quickly, not only in the outflows themselves, because when you have material that's being launched at these high speeds with high momentum and they slam into cold dust, that's going to create heating and shocks, and that will also create chemistry. And those things happen basically all the time, sometimes down to even like hours or days. And we see that also in disks as well. They can evolve quite rapidly.
Cool. Very cool. Thank you for that question. All right, we have time for one more, and then we're going to wrap up. So, Mark.
Hi there, Mark Popenchok from Astrobytes. Elena, this is my question. The asymmetry you saw was over a certain window of time in the stellar cycle. Is your result based on stacking images over that time, or do you have temporal resolution in terms of like when this asymmetry occurs within that window?
Yeah, thank you for the question. I didn't have time to go into the details. So actually, this asymmetry is found at the moment, like around July 2014, but it is integrated in 350 days, because with Fermi Large Area Telescope, that's the best instrument that we have in gamma rays. That's actually the only instrument that we have right now, and it doesn't allow to resolve the morphology day after day, but you need to integrate the exposure, actually your observations in more days. And so this is the central point, the central anisotropy is in July 14th, integrating in 350 days. But what we did, we resolved in time, meaning that we have snapshots of observations every 100 days, integrated in a longer period. So we could, in this sense, resolve in time over the entire solar cycle. So we can see an evolution of the gamma ray morphology over time. Thank you for the question.
All right, great, excellent questions. Thank you so much. That brings our press conference here this afternoon to a close. So I want to thank our PIOs for working to put together press releases for today's presentations, and also to our sponsor, USRA. And I do want to make one note that we initially had a 5th presenter scheduled for this session, Jay Lockman. If you were looking forward to Jay's presentation, make sure to be here Wednesday afternoon. Jay will still be presenting, so look forward to that. Let's thank our speakers one more time. And I hope to see you back here tomorrow at 10:15 a.m. to learn about exoplanets and brown dwarfs. Thank you.